So good morning, all of you.
Good morning, ma'am.
Morning, ma'am.
Yes, good morning.
Morning, ma'am.
Yes, good morning. So how are you all?
Good morning, ma'am.
Good morning. हाँ, I am audible ना?
Yes, ma'am.
Yes, ma'am, you are audible.
Okay, बीच में कुछ sound चला गया था इसीलिए. So in the last lecture, I think I have completed nuclear physics. Fine. वो काउंटर वगैरह मैंने ले लिया, सेंटिलेशन काउंटर और जीएम काउंटर कंप्लीट कर दिया है. फाइन.
Yes, ma'am.
ओके, प्लाज्मा स्टार्ट किया था मैंने या हाउ टू स्टार्ट?
Ma'am, बाकी था.
ठीक है. ओके, फाइन, थैंक यू. So the next chapter, it's the same chapter, nuclear and plasma physics. So the second part of the chapter is plasma physics. We are just going to see the glimpse of the topic. Okay. Detailing में नहीं जाने वाले because detailing may require one more semester because plasma is a full paper. Okay. So we'll just see some of the basic properties of plasma, the glimpse of plasma. And then we'll move on to the next chapter, right? So let me start. So what a plasma is, the non-negligible number of charge carriers makes the plasma. It is a conducting gas and they react strongly to the electromagnetic fields, right? Why, how, that we'll see later on after 3 or 4 slides. Plasma was first given by Sir William Crookes in 1879 at a high temperature, right? So all the stars, you must have studied all the stars, they consist of plasma, right? Initially when plasma was discovered, no, matlab at that time people were working with the high temperature plasma, right? People used to heat the matter and on heating the matter, the solid form of matter gets converted to liquid, gaseous, and then finally to the plasma stage, right? So that requires a high temperature. Nowadays, the researchers, they are working at a room temperature and the low temperature plasma, right? The research is going on in the low temperature plasma and the room temperature plasma, but we are going to see the high temperature plasma only. These are the few features of a plasma, how the plasma looks like. Now we know plasma is the fourth state of matter. Fine. Plasma is the fourth state of matter. Say for example, when I have a solid state, we will be having an insulator and conductor. The atoms are tightly bound with each other. The atoms are closely packed. Now, when we heat the solid, it gets converted to the liquid form, where the bonding between the atoms breaks, yeah, they becomes weak, and then finally on increasing the temperature, the liquid state gets converted to the gaseous state, and still on heating the gaseous form, we get the plasma. When you still heat the gaseous form of the matter, the ions, the electrons, yeah, the charged particles get separated from the atom and we get the ions, we get the neutral particles in the plasma state. So we need to increase the temperature. We need to heat the matter to get the plasma form. So first we have a solid form, the same thing. On heating, it gets converted to the liquid phase. Still you go on heating, we get the gaseous phase, then there will be the dissociation of the molecules, we get the atoms Still you heat the atoms, there will be the separation of the charge carriers to get the fully ionized form of the matter, which we tell as a plasma state. Now, what is plasma? Plasma is the fully ionized gas with low density, right? Plasma is the fully ionized gas with low density. Low density means as the atoms, as the ions are separated, but obvious the density of the gas will be low. So we tell plasma as a fully ionized gas with low density. It is the fourth, hello? It is the fourth state of matter, right? Plasma is the fourth state of matters. In plasma state, the electrons and ions are separately free, right? The electrons and ions are free. You can tell plasma as a quasi-neutral gas. Now, what is this quasi-neutral gas? Because see, the plasma, it consists of the positive charges, negative charges, there will be some neutral charges, there will be some solid form of the matter, some gaseous form of the matter, right? That's why it's a mixture of all the things. That's why we tell it as a quasi-neutral gas. So we can tell plasma as a quasi-neutral gas, or a plasma is a gaseous conductor and a conducting Coulomb gas. But obvious, as there are free charge carriers, Coulomb's force will be acting on the plasma. So we can tell plasma as a conducting Coulomb gas. And it is because of this property, because of the conducting property of the plasma, that it is not easy to confine the plasma. Plasma को store करने के लिए it is very difficult, right? So plasma cylinder is always kept inside a magnetic field, because see, you have the free charge carriers, right? And these free charge carriers will be moving inside the gas, due to which some magnetic field will be produced, right? So you have to keep the plasma gas in a magnetic field which is higher than the inner magnetic field. Charge carriers के motion, because of the motion of the charge carriers, जो magnetic field produce होता है ना, उससे ज्यादा magnetic field में आपको plasma cylinder को रखना पड़ता है. Otherwise, what happened? There can be the blast of the cylinder or necking of the plasma cylinder, right? Coulombian force की वजह से जो plasma cylinder है उसका necking मतलब compress हो जाएगा cylinder कहीं बीच में से, right? So we need to keep the plasma cylinder inside the magnetic field to store the plasma, right? Ionization occurs when temperature is very high, right? We get the ionization of the plasma at a high temperature, right? So this is the first part, your first topic. What is a plasma? What do you mean by a plasma? Plasma is a quasi-neutral gas. Don't write it is the fourth state of matter. Okay. Except that you can write any definition for the plasma. Now, how the plasma gas is different from the ordinary gas, right? Ordinary gas, it consists of the molecules, right? But plasma, it consists of all the mixture of all the things you can see in the in the picture. It consists of the positive charges, negative charges, neutral particles, some mu pions and muons, that are the particle which may be there inside the plasma, okay, and the neutral particles also. So let us see how the plasma gas differs from the ordinary gas. The difference between the plasma gas and the ordinary gas. You can see the ordinary gas, in the case of the ordinary gas, the van der Waals force acts between the particles. Interparticle forces are van der Waals type of force for the ordinary gas. For the plasma, there is a Coulombian force. As I told you, as we have the charged particles inside the gas, but obvious there will be a Coulombian force acting between the particles. The constituent particles are gas molecules for the ordinary gas, whereas for the plasma gas, the particles can be the electrons, neutral particles, ions, etc., etc. Right? As we have discussed, ordinary gas is an insulator at STP. matlab standard temperature and pressure. Whereas the plasma gas is a good conductor at a high temperature. The ordinary gas is not affected by the electric and the magnetic field, whereas the plasma gas is affected by the electric and the magnetic field. Why? Because it consists of the charged particles, right? And if it consists of the charged particles, it will be affected by the electric and the magnetic field. There is no effect of the magnetic field on the ordinary gas, whereas in an external, the plasma gas is affected by the external magnetic field. It behaves like a diamagnetic substance. Fine. There is no effect of the electromagnetic waves for the ordinary gas, whereas plasma exhibits strong reaction with the electromagnetic waves. So electromagnetic waves affect the plasma. Ordinary gas follow the kinetic theory of gases, right? Whereas plasma, it doesn't follow, it doesn't obey the kinetic theory of gases, right? So these are the few difference between the ordinary gas and the plasma gas. So what we have seen, what is the plasma and what are the difference between the ordinary gas and the plasma gas. Fine. Any question till this point? Okay, we will be going point to point only. ठीक है. Now see, this is a plasma illuminated by a red laser beam. Okay, you have a plasma cylinder and the laser beam is passed. You can see some charged particles. Okay, dot 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 dot. और ये illumination की वजह से you can see the particles in the screen. This is just for your information. Now, where you can see the plasma, where the plasma gas is found during the gas discharge. Okay, like fluorescent light, spark gaps, welding, bluish welding में अगर आप लोगों ने देखा होगा तो bluish color के flame या spark you can see that is plasma. Spark gaps में particularly na when in your bike na when sometimes the carbon particles get deposited on the spark plug na you might have seen that the if you just remove the spark plug and keep it on the engine and have a kick, what happens? Some flame comes out due to the burning of the carbon particles, right? So there the plasma gas is produced. In the fusion reaction, controlled fusion reaction, the plasma gas is produced. Ionizing belt surrounding the earth. Continuously the solar flares, they approach towards the earth. They come towards the surface of the earth, right? So as soon as they enter the earth's atmosphere, there is the ionization of the radiations that are coming from the space, and due to that some colorful belts are observed near the polar region of the earth. Okay, yes, the same thing, right? So they are known as an Van Allen radiation belt. So there you can see the plasma. That's why we see northern lights, right? Polar regions, yes. Near the polar region, you can see the northern lights, or it's also known as an aurora, right? Stellar in the stars, pulsars, you can see the plasma. In the solar wind, all the interplanetary medium, the plasma is seen. During the launch of a space vehicle, due to the burning of the fuel, yeah, you can tell during ion propulsion, plasma is seen. In gas laser, like carbon dioxide laser, helium neon laser, there is an existence of plasma. Materials processing during the surface treatment. We have seen materials processing in nanotechnology, like a sputtering technique, then laser ablation technique. We have seen that when during the laser ablation, yeah, during the sputtering technique, when the laser light, say for example, when the laser light falls on the surface of the target, plume is produced. right? And that plume consists of the positive charges of the target, negative charges, the vaporized form of the target material, right? So that plume is nothing but the plasma. Right. So during the materials processing of surface hardening, yeah, surface treatment, crystal growing, right? Nowadays, this branch is not as much popular, but in olden days, in 90s, lots of research were done on this crystal growing technique, right? Crystal growth technique, single crystal, multiple crystal were grown in the laboratory only. It takes 10 days, 15 days, depending on the size of the crystal. So there also the plasma is produced. Semiconductor processing like ion beam doping, plasma etching in photolithography also the plasma is produced, right? So these are the places where you can see the presence of plasma. Fine?
And
Is
there's
it
a small
okay?
correction.
Sorry?
There's a small correction. Ion propulsion is not used while takeoff. It is used in the second stage of rockets because it's a very weak way of propulsion. So it's just for maneuvering the aircraft. Sorry, the spacecraft.
Okay, that's fine. But during launching also you can see the plasma, fine?
Yeah.
When the fuel is burned. Okay, and a large amount of enormous amount of heat is produced. So this is it's okay. We'll see in the next topic. The next thing is Debye cell. Now see, people were telling that the plasma gas it consists of the positive and the negative charges, right? So just in order to prove whether it consists of the charged particle, Debye has given a very a small experiment in order to prove that the plasma consists of the charged particles, right? So what he did, he took a plasma cylinder. Let us say we are having a big tank in which the plasma is filled and two electrodes were inserted in the plasma tank, right? They were inserted in the plasma cylinder. So one will be positively charged, another one will be negatively charged. So what happens when two electrodes were inserted in the plasma cylinder, the opposite charges, they tend to move towards the opposite electrode. That is, the positive charges move towards the negative electrode and the negative charges tend to move towards the positive electrode, right? Up to a specific length. Okay, as you can see in the figure. So this the thickness of the charges that are deposited on the electrode, that he told as a Debye length, and he denoted it by lambda d, right? So after sometimes after the specific thickness, no opposite charges were deposited, right? Because of some kind of saturation. So for Debye length, he has derived the equation. We are not going to derive this. We are not going to even remember this formula. I have written it just for your information. When the charges are deposited on this electrode, no, it will be deposited till its Debye length denoted by lambda d. Okay, its equation is somewhat like this: epsilon 0 kt upon n e square. Right? K is the Boltzmann constant, T is the temperature, n will be the number of particles per centimeter cube, E is the charge of the electrode, charge of the electron, etc., etc. Fine. You got a mail regarding your LPW examination? Right. So it's online, huh?
Yes, ma'am.
Okay, fine.
Yes, ma'am.
Hmm. So this is what is the Debye shielding. स्पीयर जैसा कुछ बनता है उसको डिबाई स्पीयर डिबाई ने दिया. One more theory is that which we have given you as a self-study part, the motion of a charged particle in an uniform electric field. Okay, so that is a self-study part you have already studied in 12th standard. So the same theory you are going to use here. Okay, derivation है छोटा सा, the motion of charged particle in an uniform electric field. Okay, एक ही section करना है, नॉन यूनिफॉर्म इलेक्ट्रिक फील्ड, यूनिफॉर्म मैग्नेटिक फील्ड वो वाला नहीं करना है. Just you will be doing the charged particles in an uniform electric field. Fine. So this is what we have just seen in the introductory part, Van Allen radiation belt, right? The northern light that you can see at the polar region. Okay, so you get some ionized belt, colorful belts at the polar region, and we tell it as a Van Allen radiation belt, somewhat like this. Okay. Now an important effect for the plasma, that is a pinch effect. Pinch effect must not be there in a plasma cylinder. Okay, because of the pinch effect, there can be the blast of a plasma gas, as I told you, right? As there are free charge carriers in the plasma gas, a magnetic field is produced within the plasma cylinder, right? And due to that, sometimes there can be the blast of a plasma cylinder. So always the plasma gas is confined, plasma gas is kept in an external magnetic field so that there is no pinch effect. If we don't keep the plasma gas in an external magnetic field, no, there can be the necking SR. Okay, due to the internal magnetic field, a magnetic force, the plasma cylinder get necked. Okay, so ऐसा necking हो सकता है, या sometimes you will get a kind of hump in the plasma cylinder due to which the cylinder will blast, right? So this effect of necking, we tell it as a pinch effect. So this pinch effect is not desirable. So let us see what is this pinch effect. An electric current, it's not passed, but it is produced within the gaseous plasma, due to which the magnetic field is set up. And because of the magnetic field, the sometimes the current carrying particles will come together, right? They will be compressed, and due to this compression, the plasma heating of the plasma increases, and due to which there will be the pinching of the plasma cylinder. Due to the compression of the particles, the cylinder get compressed, right? And because of which sometimes the kinks or break will be observed in the plasma cylinder. So therefore, in order to avoid this pinch effect, the plasma cylinder is kept in an external magnetic field which is higher than the magnetic field produced inside the plasma bottle, yeah, plasma cylinder, right? So you need to keep a cylinder in a magnetic field which is higher than the magnetic field produced within the cylinder, or else simple logic is your plasma cylinder will blast. You will not be able to confine, you will not be able to store the plasma. So this pinch effect is not desirable. It is a kind of drawback, right? So we need to nullify, we need to avoid this pinch effect to properly store the plasma, right? There are few videos, but it's fine. Plasma cutting, the cutting is possible with the help of the plasma. Even the plasma gas is formed on the surface of the sun. Plasmas are formed on the surface of the sun, right? So if you wish, I can show you the video, but it's okay. ये प्लाज्मा कटर है. Let us see if it works. I need to share it. Yeah, just wait, I am sharing. So this is a kind of plasma ball.
Safe and engaging tool for studying high voltages in the electric field. A very large voltage is created by a Tesla coil-like circuit, and this creates a high electric field between the central electrode and the inner glass. Most physical science classes require that students have an understanding of plasma as the fourth state of matter. Glowing is a signature of most plasma, and so are free electric charges. On first inspection, you will notice that the plasma ball responds to your fingers. This is due to the polarization of your body, which is a decent conductor. As you approach the plasma ball, you become polarized by the electric field, and this attracts more of the free charges to you. Moving plasma can usually be controlled by magnetic fields, but this will not be visible for the plasma ball. It operates on a high-frequency alternating voltage, and because of this, the charges do not have time to get moving far or fast, so they will not get deflected. The very high voltages of the plasma ball can easily polarize a coin or piece of aluminum foil placed on top of it. By bringing your finger only a few millimeters above the penny, you will be able to elicit a spark from the top of the coin. This spark will not cause pain or electric shock, but will be hot, and if you hold your finger too long, it might begin to hurt. The tip of the finger will now show a few harmless burn marks that will rub off in a day. Use this sparking technique to explain how lightning forms due to the electric field ionizing the air. You can also touch a metal key or any conductor to the coin, and the spark will form between the two painlessly. Plasma threads are very hot, and they will rise due to their buoyancy in the other gases inside. For this reason, it is difficult to get a horizontal streamer to remain unbroken for more than a second, not unlike a Jacob's ladder. However, a vertical streamer at the top will be stabilized by the buoyancy. With practice, you should be able to get just a single vertical thread, but be cautious because the glass will heat up. The electric field can easily be investigated with a small neon bulb or light-emitting diode. Bring either of these near the plasma ball and they will light up.
See.
You can also study the globe's voltage directly by simply connecting a probe to one of the channels on an oscilloscope, and then you can probe the changing voltage spatially. Determine how the voltage decreases with radial distance by moving the probe in and out. For fun, or if you don't own an oscilloscope, you can also use an audio cable as a probe and listen to the frequencies on a pair of speakers. The human body can serve as an excellent antenna for picking up the signal, so be sure to touch the end of the cable's tip. Borrow a long fluorescent tube from your overhead lights or buy one at the hardware store and bring it near the plasma ball. You will notice that once a part of the mercury gas in the tube gets glowing, that it can stay glowing even as you extend it. There is essentially no limit to how far you can pull the tube. At certain distances, however, the tube will not glow. There is a minimum electric field required to ionize the mercury gas, and if the field is not strong enough, the tube will not light. It also works on the small household tubes. Demonstrate that the electric field can be diverted to a grounded shorter circuit if you grab part of the tube. This will reinforce the idea that lightning and other currents, perhaps later on, take the path of least resistance. Look straight at the plasma globe and place a finger as far to one side as possible. Analyze this with your diffraction grating and compare the spectrum to known inert noble gases. The vertical column will be ideal for analyzing its spectrum. Different globes use different gases in different amounts, but they're almost always noble gases. Now you can put ionized neon tubes in the hands of eager students because your plasma ball ionizes them safely. No longer is a black box needed to confuse students as to what is happening. The plasma globe's strong electric field rips the electrons off their atoms, and unique colors are produced as electrons are reacquired by the various orbitals. Teaching about the emission spectrum of ionized gases can now become a hands-on activity. A plasma ball provides a safe source of high voltage that can allow you to investigate the properties of a cathode ray safely. Teacher and student alike can now safely and easily demonstrate magnetic deflection of electrons and relive the discoveries of J.J. Thomson thanks to the marvelous plasma globe. In conclusion, the plasma globe is an underutilized and relatively familiar piece of lab equipment. I strongly recommend that every physics teacher include one in his or her laboratory and use them to make studying electrostatics as hands-on as possible.
So few properties of plasma were discussed. Even this plasma cutter is a good video. How the plasma gas is used for cutting an aluminium foil.
Hello there, welcome to this episode of the Slow Mo Guys. In this video, we're doing a lovely scientific experiment where we're going to make our own little plasma cutter using pencil lead, 4 batteries, and some aluminium foil. They spell aluminium wrong. Okay, so the way this works, you connect the batteries in series. Connect one side to the foil, and the other side, pencil lead. This. I record this on the Phantom Flex, 2,500 frames a second, macro lens, so we should be able to see something up close, really nice. Enjoyed that video. I quite like shooting stuff in macro. It's very fiddly, but you get extreme close-up slow-mo, which I think is very cool. And in science experiments, you can add General Electric to Snapchat, and if you send them an emoji on December 10th, they may just send.
I think this is the video of solar plates.
Is there plasma in a plasmid?
Right? Even few more are there, but it's fine. I will not show that. It will take time. So only some basic things that we have seen in this topic. What is plasma? What is the difference between the ordinary gas and the plasma gas? Where you can find the plasma, Van Allen radiation belt and the pinch effect. Then after the motion of a charged particles in a uniform electric field, right? One simple formula is there that you will be deriving. That will be the self-study part for you. Fine. And with this, I think I can move on to the next topic. That is, I'll be mailing you both the PPT. I think I have not mailed the counters and this one, plasma, I'll be mailing you, right? And even I have the recorded slide also. That also I can mail you. So we'll be we'll be starting with the next chapter, that is physics of vacuum technology. Right? This is having a weightage of 6 to 7 marks in a 100 marks paper. So in this chapter, we are going to see or will be studying 3 vacuum pumps and a gauge. That is, a gauge is a device that is used for measuring the pressure. Right? So first of all, what is a vacuum or what a vacuum is? It is the reduction of a pressure in a container by vacuum pumps. So what we are going to do is how to reduce the pressure of a given assembly, of a given container, right, by different types of vacuum pumps, and what will be the value of that pressure. Okay, So a low pressure is a vacuum. Decreasing the pressure in a given assembly creates a vacuum, right? So these are the different units of pressure: mm, Hg, Pascal, bar, torr. You might have used all this unit, right? So vacuum is nothing but it is a low pressure, right? So these are the different units that are used in vacuum technology, right? So this is our moral supporter during the tire puncture, right? So there is a puncture in your vehicle, right? We use, particularly for the four-wheeler, we use this for measuring the pressure inside the tube. So these are the various relations between different units of pressure. You just go through this. 1 Pascal is 1 Newton per meter square, etc., etc. Okay, so have a look at this conversion also. Now, there are 4 types of pressure levels, yeah, vacuum levels. First one is a rough vacuum. As I told you, see, whenever the vacuum is to be created during sputtering, yeah, laser ablation also, I must have told you, if we require a high vacuum, directly we cannot go to the high vacuum. We have to start with the rough vacuum. Fine. So a rough vacuum, medium vacuum, high vacuum, and the ultra high vacuum. Right. So these are the different ranges of the vacuum. Now, where you can see where the vacuum technology is used: food packaging, beverage industry, cleaning purpose, thermal insulation, cathode ray tube, right? Where in food packaging, to remove the air molecules inside the food packet, vacuum technology is used. Packaging, okay. In the beverage industry, bottle filling machines and soft drink plants, the vacuum is used. Deaeration of the mineral water, okay, to remove the carbon dioxide from the water, the vacuum technology is used. This all of you must be aware of. Vacuum cleaners, thermal insulation in between the two walls of a thermal what you say, utensils, yeah, thermal wares, the vacuum is used. Now, how to produce the vacuum? See, this is the main part. We are going to study 3 vacuums, like rough vacuum, mid high vacuum, and the ultra high vacuum. What is the range of a rough vacuum? Up to 10 to the power minus 3 torr. High vacuum -4 to -6 torr, and ultra high vacuum -7 to -12 torr. Right. So for creating the rough vacuum, the rotary pump and the mechanical pumps are used. That is known as a roughing of a device, right? So जो excess amount of air molecules है ना, वो remove करते हैं, and that is known as a roughing, right? So for rough vacuum, the rotary pump and mechanical pumps are used. We are going to study the rotary pump as per our syllabus. For creating the high vacuum, diffusion pump and the turbomolecular pumps are used. We are going to study the diffusion pump. For creating the ultra high vacuum, ion pumps or cryo pumps are used. We will be studying, I think, we will be studying the ion pumps, right? So as a whole, we will be studying the 3 pumps in our syllabus: rotary pump, diffusion pump, and the ion pump. For measuring the rough vacuum, thermocouple gauge या Pirani gauge is used. These gauges are the devices which measure the pressure, which measures the pressure of a given container, या given area, a given space, right? And Bayard and Alpert gauge is used for measuring the high vacuum and the ultra high vacuum. We will be studying the thermocouple gauge and Pirani gauge. Okay, Bayard Alpert gauge we are not going to study. So in order to obtain the vacuum, different types of pumps are used. different pumps are like gears on a car, right? As I told you, suppose if I want to go for an ultra high vacuum, directly I cannot go for an ultra high vacuum. I have to do the roughing. Roughing के बाद I have to go for the high vacuum. वैसे तो roughing के बाद we have to go for the medium vacuum. Medium से के बाद high vacuum, and after the high vacuum, we need to go for the ultra high vacuum, right? So just like the gears of a car, right? Top में जाने के लिए सीधा you cannot go to the top gear. You have to start from the first gear, second gear, and so on, and you need to go for the top gear, right? So similarly, for creating the vacuum also, few steps are to be followed. Different categories of vacuum pump, gas transfer pump and the entrapment vacuum pump. This rotary pump, it comes under gas transfer vacuum pump. There will be the transfer of the vapor from hot region to the cold region. We'll be seeing that, right? So that is a positive displacement pump. So we are not going to we will not be seeing all this category. This we have given just for your information. So rotary pump is an example of the gas transfer vacuum pump, and diffusion pump is also the example of the gas transfer, but then the fluid will be using a hot oil. So with the help of the vaporized oil, the molecules of the atmosphere will be trapped, right? So that will be seeing. So rotary, diffusion, and then the entrapment pump, cryo pump, which we are going to see, is an example of an entrapment pump. The ions will be trapped in a grid, okay, and along with the ion, the gas molecules will also come because we are going to apply the electric field and the magnetic field in this pump. So that will be seen. So the first type is a rotary pump, which is also known as a rotary vane pump. I think I will start from the next class. 3 pump ho jayenge. Okay. So I will mail you this PPT also. एंड जो आपकी स्प्रेडशीट है ना, उसपे मैं एक रिकॉर्डेड लेक्चर भी रख दूंगी ये वैक्यूम टेक्नोलॉजी का. ओके, आई शेयर अ लिंक इन योर sheet, so you can just go through that recordings, and then we will have the in the next class I will take this box, right? Fine. So thank you.
Thank you, ma'am.
Yeah, welcome.
Thank you, ma'am.
Yeah, welcome.
Thank you, ma'am.
Okay, bye. I'll जब recording में रखूंगी ना ये lecture का, उसके साथ ही मैं link रख दूंगी, so you can watch the recorded lecture of this chapter. Okay. उसके बाद next lecture में I'll be taking एक बार